I'm going to begin with a few introductory remarks since this is our first official meeting. We will always meet first in SBA 240. That is the lab lecture room. We'll always start there, so please come to that room every time. We will adjourn after some initial discussion and activities we perform. We will then go to the laboratory where we will conduct business together. But please always come to SBA 240 to start. Okay, you can see below there my office hours. I have various office hours at different times. If they don't fit with your schedule, maybe we can work something out in addition by appointment. Or, believe me, there's lots of times in the laboratory as well when you finish and I'm still there with other students. Maybe you could straighten up any issues you would like with me right there that without having to do anything further. Of course, you could send me an email as you see at the spot on the Southeastern mail delivery system. I posted the schedule of the laboratories we're going to perform on Canvas. You can download a PDF of that. As a matter of fact, you can download the syllabus from Canvas as well. We also have it posted on the Southeastern Chemistry Department page, but it's easiest to get it from Canvas. Now look, please be very clear about this with me. You have to have the lab manual. You can't have another version of the lab manual somebody else gave you because probably the data sheets are taken out of it. That's the main thing that are going to be missing, and that's the main thing that are going to be important for us. So please go to the bookstore, purchase a copy of the Chemistry Lab 1240 lab manual for the class and have it with you next week. We will begin to gather data and go into the laboratory next week, so please make sure you do that and make sure you have your own individual copy to use to collect your own data and submit your own reports. Okay, there will be lab reports for each of the laboratory exercises we do. That will be 1/4 of your grade will be determined from your lab report grades. Of course, much like you did in 1230, the previous semester laboratory, we will work with partners on many experiments, and there might be times where we will work individually, particularly on the practical part of the exam. So when we work with partners, which will be most of the time when we do these lab reports, you and your partner can submit a lab report together, because what we're going to generally do is upload our reports to Canvas, and as long as you and your partner's name are clearly marked on the lab report, that will be sufficient. Now, I will be pointing out very explicitly the details of how and the submissions should go, whether we will submit them on the forms in the classroom or if they will be uploaded on Canvas. It actually depends individually on the lab reports and the format of each lab report that we do. So believe me, I promise I will be very clear about that. Again, you really only need to submit a report for your team of 2 that work together on the lab. That will be sufficient. Of course, you will both receive the same grade for each of these lab reports that you work with your partner. Okay, in addition to that, just so I make sure that one person is not lifting all the weight and the other person is just slacking and letting the other person do all the heavy lifting and all the work, there are quizzes that go along, and these quizzes will be mostly again taken at the beginning of the class period. By the way, we will have one at the beginning of the next class period for sure, covering the items we talk about later in the slides. So these quizzes will again total for 100 points, and they are again 1/4 of the grade in addition to the 1/4 of the grade from the lab report. And they are given notice very explicitly at the beginning of the period, not 10 minutes into the period, not a half hour into the period, not at the end of the laboratory period. they start at the beginning of the laboratory period. So whatever time your class starts, your lecture class in room SBA 240, you better be there because I'll be giving them out the clock strikes class time to begin. So these quizzes again will total 100 points. None of them will be dropped, and they will be detailed in the way the calculations are done for the laboratory. Now again, the point is that if you work with a partner on the lab report and you don't do any of the work, you let the lab report be done entirely by your partner, you're still going to be obligated to be familiar with the calculations that go into the lab report through the quiz. I will be very explicit about what the quiz questions will be based, especially on, they're essentially based on the calculations we do to complete the lab report. So you have a very good idea what kind of calculations will be on there, and I will point those out to you as we go along. Okay, so if you come to class late, as you see there, and the quiz is done, I'm sorry. You have to be there at the beginning of the period. That's when the quiz starts. And once it is over, it is over. So please come to class on time, and then you can be sure to do your quizzes. Now, one of the good things about the quizzes is that after we complete the first 4 laboratories, we're going to do our lab midterm. The questions from the quiz are essentially much, or not all, but a good deal of the material that will be covered on the midterm and the final exam. So the quizzes, in a sense, give you some indication of the kind of problems I'm going to be asking when we do the midterm and final exam for the class. Sorry, I'm trying to stop my audio here, and I'm having a little bit of difficulty. Bear with me here. For some reason, my mouse decided to disappear. It must have been auto-saving, and I was. So, the lab reports will be 25% of your grade. The quizzes will be 25% of your grade. There will be a midterm covering the first 4 experiments, and a final plus a practical covering the last 4 experiments. Now, the midterm will only be, I believe, online from Canvas. You can answer the questions for the midterm on that. The final has a Canvas component as well, but it also has some skills that you have to demonstrate in the laboratory directly. So 50 points of the final exam will be online from Canvas. 50 points of the final exam will be practical, where you will do laboratory activities at the very end of the semester. So each of those sections are going to be worth 100 points each. There'll be 400 points total. And so then your final grade will be determined based on the 10-point scale, of course, 90 to 100, or a total of 360 points or above A, 80% to 89%, or 359 points down to 320 points for a B, above a 70% for a C, which means between 319 and 280 points, and so forth. The next item mentions the calculator policy, and the calculator policy is quite simple. You need your own calculator. Calculators will not be shared. You cannot use your smartphone as a calculator. You need a dumb, regular, scientific type calculator that has exponentials and logarithms in order to do your activities on the quizzes and the practical, that's for sure. So make sure you have your own. Then the next item on there talks about the fact that this class is in support of Chemistry 1220, the second semester general chemistry class for science majors. The laboratories are designed to accentuate ideas from the coursework in that class. You don't technically have to be simultaneously enrolled. As a matter of fact, the material won't exactly match the the time when you're covering it in lecture compared to when we do it in lab might not line up perfectly anyways. But this statement is trying to say you're supposed to have some basic excuse me, background knowledge in order to complete the laboratory. The next item is laboratory safety. Safety is the number one priority in the class. Now, believe me, we're going to try whenever possible to use safe materials, and we're not going to be doing hazardous experiments per se. However, we're going to be using hot plates and water, and the floor could get slippery. We'll use a lot of glass implements that could break. So if you exercise similar caution that you would exercise in your kitchen, then that's really about the level of danger we're going to place you in the laboratory. However, we still have to follow the safety protocol of the department. This requires that you have safety goggles on at all times. Now, you might lift them to make a reading off a device or something like that, but otherwise you should be wearing your safety goggles. You should already have been issued safety goggles from Chemistry Lab 1230. Any students who weren't in Chemistry Lab 1230, I have a list of those students, and I will be giving them their own individual copy of the laboratory goggles. Otherwise, you are responsible for your own, and I believe you can get them if you can't find the ones you were given last semester or whenever you took 1230, then you can buy them at the bookstore. But please make sure your clothing you wear properly covers your body. No open-toed shoes. It's best that you don't have to wear long pants, but it's always a good idea to wear long pants in the laboratory. And if you want to wear sleeves covering your arms, fine. We have safety gloves available, and you should always, again, be wearing your safety goggles. Certain chemicals that we use in the laboratory have certain levels of danger associated with them. These are detailed on what is known as the MSDS sheets, material safety data sheets, that accompany these products. When we are using such things, you will be familiarized with the hazards that they pose, so that anybody that has particular chemical sensitivities can be aware of the kinds of issues that might arise in handling these chemicals. Again, if they are of any type of danger at all that they could pose to you, they will be handled in a hood, and you will do them in the hood, and then you will complete the protocol of wearing gloves and having your safety goggles on when you dispense them, so that there's no chance of any injury. If you do have any known chemical sensitivities, please let me know ahead of time. If you happen to become pregnant or know you are pregnant, that might also be a good idea that you inform me about that, in case we are happen to be using materials that might not be good for prenatal situations. So if you do happen to know anything about any chemical sensitivities you have, please let me know so we can be extra careful when we happen to handle those particular chemicals. All right, now attendance in the laboratory is mandatory. There's not makeup labs. We're on a very tight schedule because of the large number of students that run through the Chemistry 1240 lab program. We have people who set the chemicals up, bring the chemicals out, put the equipment out, and then when everybody has completed the activities, these are broken down and the next laboratory setup is placed in the room. So it's almost mandatory that you come to the lab class that you're assigned to. Now, as a matter of fact, I'm teaching 3 sections of 1240. One of them is on Tuesday, one of them is on Wednesday, and one of them is on Thursday. But they are all full sections that currently have 24 students enrolled. This is the fire marshal's limit of students that are allowed in the laboratory. So you must attend your own session, and you must attend it the week of that particular laboratory that we're performing because the equipment is broken down, put away, and chemicals are disposed of. So there's no availability of doing any makeup. So it is possible that you might be able to attend another session if you know in advance that you're not going to be present for our particular period. But otherwise, please do your darndest to come to our session, because if you miss your session, you're going to not be issued any points for the laboratory report that session was dealing with. You're going to miss a quiz in the class, more likely than not, that you're not going to be able to make up. So please make sure you come to class on the scheduled times of the laboratory. If you have any known accessibility issues, then you are given accommodations to offset your accessibility issues, but these are not automatically granted. You must petition the university through the Office of Student Life or Student Success Center to complete the forms, and then they send me what accessibility issues are to be met. And so if you do have such requirements, please begin the process of completing the forms so that all that can be in place when we start to do our work in the upcoming weeks. The university requires I make a statement about acting up in class. Don't be mean to me or yell at me. You can make jokes about me behind my back. That's okay. But please, let's act civil towards one another. Please try to respect everybody in the class and be respectful of each other. And I don't really have anything else to say about that. With regard to academic integrity, as I mentioned earlier, you're allowed to work with your partner or even other groups if you'd like on your lab reports. That doesn't bother me at all. However, on the graded assessments of the quizzes and the midterm and finals on Canvas and the practical exam at the end of the semester, you're going to be on your own. So please make sure that you adhere to the policies of the university in that regard. Now also, we've already had our first emergency contingency because of the way we're delivering this particular class. If any other cases of emergency contingency arise, tune into the university webpage and they'll tell you when and what we're going to do, and then through Canvas we will possibly be able to communicate that. That's just like we're doing now. All right, the drop date for this class is Friday, April 4th. By that time we will have had several quizzes, at least 4 I would say. We will have 4 lab reports under our belts. We'll have our midterm exam certainly completed by then. As a matter of fact, we'll be pretty much near the end of the semester by this time, so you will certainly know where you stand. Now, I don't really care if you're in the 1220 class or while you're taking the 1240, if you want to drop one or the other. I guess that's up to your own individual needs. But please be aware that I don't remove you from the class. You must remove yourself by Friday, April the 4th. Okay, so that's the preliminary stuff. Let's now get to the meat of the matter for what we will need to do for our first quiz next week. And essentially, this is a review of things that should have been covered in your 1230 class with regard to the way information is reported in the scientific world. Now, let's be very clear. Scientists are very rigorous. There's really not room for flourishy talk or trying to be prosy when you're speaking or writing reports to everybody. Technical writing is written very tersely and very concisely and right to the point. And when we make reports, generally reports are focused around numbers, because measurements are all about numbers. So we have strict rules for interpreting and understanding what these numbers mean. And the basic idea, the basic premise behind this is because all measurements are real numbers. Being a real number means that it has infinite significance, or it has digits to all degree of accuracy. Of course, there are limitations based on the measuring devices that we use that cause us to limit the significance or the number of accurate digits that we can gain from a particular measuring device. So what we're going to do here is first review the rules for significant figures, and we're going to apply these rules as we write our reports during the course of the laboratory. Again, this is something that should have been done in your 1230 class, so this should simply be a review for you. But there will be a quiz next week on these various issues that we cover here. So let's make sure we're clear on the various issues. Again, the reason we need to do such things is that we're dealing with numbers, we're dealing with measurements that are based on numbers, and these numbers are naturally going to contain error. Now, the error can arise in a couple different ways. It could be because you're using a faulty measuring device that doesn't read correctly. It could be because you don't know how to use the device you're getting a number off of. Just flipping the switch on and the number shows up on the dial doesn't necessarily mean that you've used the measuring device in the proper way. So if you don't know how to use the measuring device, it could give you a reading that is not correctly representative of the property you're trying to evaluate. But let's say even if you are trained in how to use the device, even if the device is working correctly, there is still going to be error in the measurement. And that is because, again, the measurement is a real number. Our device cannot record a real number to its infinite degree of significance. So there's a limit to the degree of accuracy to which we report a number, and that is known as the significance of the measurement. So let's review the rules for significance. So there will be questions next week that have numbers in them, and one of the things you'll be required to do is to report to me how many significant figures these particular number representations represent. Okay, so quite simply, if a device reads out anything but a 0, it is assumed that that is a significant figure. All non-zero values are what, when you turn the device on, the device should be reading 0 if it's not measuring. Once it starts measuring, the values go to numbers other than 0. And so any number that shows up other than a 0 is a significant figure. Now, what you will then note is that there's a truncation point in the degree of accuracy of the digital readout on the device, and we can only assume that that number should have been continued on to infinity. So only one of two things are then possible. The device either rounded up, making the last digit that it shows a little bigger than it should have been. Like say it was 1.23 it shows, and the actual number was 1.229999999. So it rounded up, making the number a little bigger. Or it rounded down, truncating off something. Maybe it shows 1.23, and the actual readout was 1.231111111. So either the number it shows is a little too big or a little too small, even if it's reading correctly. Now then, you have to be able to interpret and recognize where the error is in the measurement. We were assuming on a digital readout that the error shows up in the last digit, and we will point this out again a little later in the period, but for now let's make sure we understand. The last digit is in some way incorrect. How incorrect is it? Depending on the tolerance of the measuring device. The manufacturers will issue a value that indicates this tolerance, and maybe we can see that on a slide upcoming. So for now, if we have a readout of, as we see there, a number that shows for instance, 1.1159 on the digital readout, that would mean it is accurate to 5 digits of displacement. The decimal point means nothing. Above that, you see 1,376 as a readout. That number, even though there's a comma, it doesn't matter, has 4 digits of accuracy. And as you see, then finally a number with commas and decimal points, all non-zero values are significant. So that reading on the very bottom has 8 significant figures. Now, I would like to point out to you, any measuring device in this laboratory is nowhere near going to approach 8 digits of accuracy. The best we're going to be able to do is probably a 4-digit accuracy readout. And if you see numbers like that, that's usually an indication that either somebody spent a huge amount of money to make the measurement, or they don't understand how to report the significance of the measurement. Now again, there is inaccuracy in these numbers. They're in some way random, truncated in the last digit, so that there is error in that last digit. Maybe it was truncated off, maybe it was rounded up. And then again, to really get the full grasp of the spread of the possibilities of the answers, you should maybe consult the manufacturer's tolerance that tells you in that last digit how trustworthy the value is. The trouble really comes in when the readout still has zeros on it, because you have to be able to now interpret whether or not the zeros displayed on the readout are part of the measurement or simply put there to make the number fit the unit scale that the measuring device is reading out. Now, hopefully we'll see what I mean by that last statement here in a moment. But suffice it to say that when a readout shows zeros, you have to be a little careful as to whether or not the zeros are part of the significance or not part of the significance of the measurement. So let's do the easy zeros first. Any zeros between non-zeros were part of the digital readout of the scale. So as long as they're bracketed by non-zeros, you can make the assumption that the digital device spitting out the value included those zeros in its measurement form. So the number 407 has 3 significant figures with a significant 0 between the 4 and the 7. Likewise, 2.068 has 4 significant figures, whether it's to the left of the decimal point or the right of the decimal point between the non-zeros. Doesn't matter. 6.00005, 6 significant figures. And then, as you can see there, a number with commas. As long as it's bracketing numbers with zeros between non-zeros, you count all digits as part of the significance. Once again, these are not completely accurate numbers. They would have to be infinitely significant, read out to all possible values in order for that to be true. So this truncation causes a limitation to the significance. Another type of good zero, one that counts towards the significance of the measurement, is provided by a 0 at the very end of a number following the decimal point. Let's be very clear. At the end of the number following the decimal point, we are going to assume that the measuring device is placing that digit there with that 0 in it in order to show you the place to which the device is reading accurately. Remember, that 0 at the very end is an incorrect digit. There's some truncation in that 0. Yet the device has to show you the place where the error begins. Now again, this only is the case when the zeros are padding a number after the decimal point. Let's be very clear about that. So 6.0, that 0 was put there because the error is in the tenths place of the measuring device. Maybe the correct number is 5.9999999, which the device has rounded up to 6.0. Maybe the correct number is 6.01111111, which the device has read out as 6.0. So there is error in that last digit that they're showing there, always. Now you'll notice in every case, you have zeros at the end of a number past the end of the decimal place. Those, again, we're going to assume are placed there by the measuring device in order to show you the place to which the error in the measurement begins. Even as we see in the third case down, in the fourth case down, we have multiple repeating zeros. Then the last one that's shown is where the error for that measurement begins. Now let's talk about some bad zeros. The first type of bad zero is a zero which is after the decimal point but pads the number to push the value down, the non-zero values down to lower decimal places. Those are padding zeros, as we call them. They precede the non-zeros, and really it's a problem with the measurement unit scale. As I show in example number 1, how we can change and eliminate those padding zeros that are after the decimal place but before the non-zero. Now remember, on the last example, they were after the decimal place, but they were after the non-zero. Here, they're after the decimal place, but before the non-zero. What is bad about those is that they're simply trying to display the value on the unit scale provided. As you can see in example number 1, you can eliminate them by changing the unit scale. 0.002 grams, if instead read out in milligrams, would be 2 milligrams, because there are 10 to the minus 3 grams in a milligram, or 1,000 milligrams per gram. So I can eliminate them by changing the scale from grams into milligrams. 0.031 kilometers, you can see when placed into meters, since there are 1,000 meters per kilometer, I'd multiply 0.031 by 1,000. That would be 31 meters, eliminating those padding zeros to the right of the decimal point. Another way of eliminating these padding zeros is to report numbers in scientific notation. Now, we didn't speak directly about how to write numbers in scientific notation, but I'm assuming in 1210 and 1230 you did scientific notation, you're familiar with how to use scientific notation. So we see, for instance, the value 0.0375, which is can be rewritten in scientific notation as 3.75 times 10 to the minus 2. And as a matter of fact, when you read a number in scientific notation, you follow the rules for the number component to get the number of significant figures it displays. So that is representing that number in scientific notation with 3 significant figures and eliminating that padding 0. The final example, 0.000046, if expressed in scientific notation, is 4.6 times 10 to the minus 5. All those padding zeros have been eliminated. Now another way you could do that, let's suppose the 0.000046 is in meters or something like that. I could change that to 46 micrometers would be the value if I changed the unit scale on that, and I could eliminate those padding zeros in that fashion. So if I were to present to you a number with zeros to the right of the decimal point, but be preceding or before non-zeros, you eliminate those types of zeros when you're counting the significance of the measurement. So the value 0.0000006 is really a one significant figure reading value. It could be written 6 times 10 to the minus 6, as a matter of fact, eliminating all those zeros. 0.01005. Now, in that case, the padding 0 to the left is no good, but remember the rule for zeros between non-zeros, those are good. So I'd have to include those so that there are 4 significant figures in that value. Again, that could have been written 1.005 times 10 to the minus 2 if I wanted to write it in a correct way of eliminating that padding 0. Then the value 0.0030000 has 6 significant figures. The 5 zeros following the 3, according to our earlier rule, would be placed there by the measuring device to indicate where the error begins. It begins all the way in that last 0 that you're presented on the measurement scale. However, the padding zeros before the 3 that precede the decimal point could be eliminated by switching to scientific notation. So something like 3.00000 times 10 to the minus 3 would eliminate those 2 padding zeros before the 3 in that number readout. Another type of bad zero is in a number that has no decimal places and you have zeros following non-zeros. Now, a lot of people, what they will do is to show if these are good or not, they will put a decimal point in there with nothing after the decimal point. I'm not a big fan of doing it that way at all. I would prefer to show you the significance of the readout by changing either the unit scale or using scientific notation. You see, for instance, if these are just purely padding zeros in the value 400 milliliters, I could eliminate those padding zeros by changing the unit scale to liters. If instead I had a value like 30,000 and I have knowledge that only the 3 is good, but on the unit scale I'm using, I needed to pad the number out to the value shown, then I could eliminate all those zeros by presenting that number in scientific notation as 3 times 10 to the 4. Now, if I had listed 3.0 times 10 to the 4, that would mean one of the zeros was actually part of the measurement. If I had listed 3.00 times 10 to the 4, then 2 of those zeros would have been part of the measurement. If I'd have listed 3.000 times 10 to the 4, then 3 of those would have been part of the measurement. And finally, if I had listed 3.0000 times 10 to the 4, then I would conclude that all of the zeros, even though they're really padding the value, would actually be part of the measurement. What I like to call these kinds of zeros is that they are zeros that cannot be determined. In the form written, you simply can't tell whether the zeros are significant or they are not, unless you convert the number onto a different unit scale or unless you use scientific notation. Again, the 400 milliliters, let's say none of those zeros are good. In liters, I would write 0.4 liters. The 400 milliliters, if the first 0 following the 4 was actually accurate to the measuring device, and that's where the error begins, then I would list it as 0.40 liters. That gives me 2 significant figures of the proper format. Let's say all 3 of those numbers, the zeros inclusive, were part of the measurement so that the error begins in the ones place on the milliliter scale. Then to get rid of the ambiguity as to whether or not those are error, those contain error, I would list it as 0.400 liters. That puts the unambiguous type of zeros into the display. So if you see numbers of this type, my best answer is I cannot tell whether they are significant zeros or insignificant zeros in the way the number has been presented. As a further example of these padding zeros and their ambiguity, suppose I have the number 4 million. If that number has an unknown amount of those zeros of accurate or inaccurate origin, how do I correctly write 4 million so that the interested party has an idea to the trustworthiness of the particular number I'm reporting? If I write 4 times 10 to the 6, that would mean that all those zeros that were included there were simply put there to shove the number out to 4 million. Now, what would be an example of something like that? Say I have a computer with 4 million bytes of data, but it only is accurate to that 4 value there. I could present that as 4 megabytes or 4 with no decimal point times 10 to the 6 bytes. Those would be the ways to accurately portray that. Now let's suppose one of those zeros is accurate, the one immediately following the 4. So instead of writing 4 million with its ambiguity, I could write either 4.0 times 10 to the 6, or if again this was in bytes as 4 million, I could have written 4.0 megabytes. For 3 significant figures, I could report 2 zeros following the decimal point, which are the good forms of zeros, if I do it in scientific notation form. But again, suppose it's bytes, and I have 4 million bytes with 2 good zeros, I could write 4.00 megabytes. And then we can just continue this process as more and more of the zeros become significant until I finally get to a 7 significant figure representation of 4 million as 4.000000 times 10 to the 6, or 4.000000 megabytes. In lab, we very commonly not only report numbers of significance, we manipulate them. We add, subtract, multiply, and divide the values. So what are the rules of combining values of significance? Well, first of all, you have to be able to recognize how many significant figures are in a particular number representation. We just showed how to do those things. Once you have figured out how many significant figures you have present, and now I'm going to combine the numbers of significance under mathematical operations, how and what rules do I apply in order to do so? Let's start with the easy one. Adding or subtracting, which are really the same mathematical operation. Subtracting is just adding a negative number to a value. So really they're technically the same thing. So the rule quite simply is that when you add or subtract measured quantities, first of all, let's be clear, they have to be in the same units. You can't add liters to milliliters. You can't add grams to kilograms. For that matter, you can't add volts to watts. Whatever you are adding must be in the same units on the same scale. You can't add minutes to seconds. You can't add milliseconds to kiloseconds, but you can add femtoseconds to femtoseconds, and that's it. Why? Because then you're lining the decimal points up correctly on the same numbers when they're in the same units. So first, they must be in the same unit. Then what you do is you look at where the last digit of the numbers shows up, because that is, if done correctly, where the error shows up. So for instance, adding 4.8713 and taking away 2.15 from it, then the 2.15 has an error in the hundreds place. The 4.8713 has error in the 10,000th place. So when I go to combine those numbers, the error propagates, as we say, from the number of least significance to a position in the calculated value where the error shows up due to the presence of error in the least significant number. So the bottom line is, when you add or subtract numbers, the error in the result shows up at the same position as the error in the number of least significance. So when I combine 4.8713 and subtract minus 2.15 from that, I should report 2.72 and not put those remaining digits behind it, because the person I'm reporting to would have no idea as to whether or not all the digits were combined correctly in the addition or subtraction unless I showed them the mathematics that I was doing to report that number. So you truncate the result. You could round if you would like. I typically just go, I might round if the number that I'm lopping off is particularly large, but you can just truncate because the answer has error in the same position anyways. So the answer you should get is 2.72 when you combine those values. And as I say at the bottom again, you can either truncate or round off the extra digits depending on what you would prefer to do. So here's a few examples of doing such things. I'm combining 35.1 with 2.4846. The 2.4846 was measured to, if you like, 5 digits of accuracy, where the 35.1 was only measured to 3 digits of accuracy. The 35.1 to 1 decimal place, the 2.4846 to 4 decimal places. It's just simply a waste to do all that extra work to get those extra decimal places in the second number, because the error begins in 35.1 in the 10th place. So the error of the combination of the two begins in the 10th place as well. So you should report 37.6. Notice in the second example, I'm subtracting 1.73 from a much highly more accurate number, 2.00817. I do the subtraction as normal, but then I truncate the result to show error beginning in the hundredths position, just like the error in 1.73 is assumed to be in the hundredths position. Now notice that, interestingly, in the last example, I'm combining a number with no decimal values with a number with a single decimal value. There is error in the 9 of the 449 if reported correctly. There is error in the 2 of the number that you're combining it with. So when you combine the numbers, the error shows up where error is originally located in the first decimal place possible that error can exist, and that is in the ones position. So the combination of those two should correctly be reported with no decimal places, since error in the first number was in the ones position. Now multiplying and dividing is a little different. First of all, let's be clear. Unlike adding and subtracting, multiplying and dividing measured quantities, they do not have to be in the same unit form. Okay, again, when you add or subtract, you must have the added or subtracted quantities in the same units. You can't add Fahrenheit to Celsius. You can't add kilograms to meters. You can't add millimeters to micrometers. They have to be in exactly the same unit form to add or subtract. That's not true at all in multiplying or dividing. You can multiply any number of any unit by a number of any other unit. It just shows up in the combination of units. Whatever you do to the numbers, you do the same thing to the units. So here I have a mass of 26.57 grams. I have a volume of 21 milliliters. Now, of course, let's assume these are reported correctly numbers. The volume unit has an error in the ones position for that particular unit form. The mass unit has an error in the hundredths position, 26.57. The error begins in the 7 in that particular value. So now I want to combine the values by dividing the volume into the mass to give the density. Now notice, first of all, when I do so, I'm of course going to divide 26.57 by 21, but I'm also going to divide grams by milliliters. I report units of gram per milliliter. Please be aware, whenever we combine units under combination of multiplication or division, that you do the mathematical operation on the units. But now let's note, when I do these values in my calculator, it spits out, because my calculator only reads out the 8 digits, 1.2652381. And if I write that number down, that's an indication of way more significance than the value I actually worked with. There's way more presented digits in the calculated form compared to the measured forms I worked with. That's not possible. The number you result with cannot possibly be more accurate than the numbers you began with. So what is the rule as to where I truncate the calculated value of a combination of values of significance? The general rule we apply is that you count the significance of the numbers that you're combining under mathematics of multiplication or division. You perform the mathematical operation, then you truncate or round the answer to the same number of significant figures as the value that had the least number of significant figures. Now, this is a little different, subtly different, than adding and subtracting. In adding and subtracting, the answer has as many decimal places as the value with the fewest. Here, you could be combining numbers of varying degrees of decimal places. What you do, though, when you combine them, is that you count the significance of each, and you limit the significance of the answer to the value with the least number of significant figures. So when I took my mass of 26.57 grams and divided by a volume of 21 milliliters, since the volume had 2 significant figures and the mass had 4 significant figures, the mathematical operation gives me a crazy long 8 significant figure number, but those digits are not all significant. I show the same degree of significance in the answer of the density as the least significant measurement, which was the volume of 2 significant figures. So I'm going to round the density value off to 2 significant figures of accuracy and report 1.3 gram per milliliter. So why does the rule of combination of multiplication and division differ from the rule of combination of addition and subtraction? Well, let's just look at this little example here that will try to demonstrate what the problem is in the multiplication and division case. Here I'm I'm calculating the area of a square. It's not really a square, it's a rectangle. Why is it a rectangle? Because its length and width are different values. So someone has measured the values to be 3.7 centimeters and 5.2 centimeters. Of course, if these are reported accurately, they both reflect error in the tenths position. They are each 2 significant figure values. So according to the rule, when I multiply them together, the answer should have 2 significant figures. So when I take 3.7 times 5.2, my calculator spits out 19.24, and I'm saying that should be only reported to 2 digits of accuracy. Now, let's note something else of great importance. Not only did I multiply the numbers together, I multiplied the units together. 3.7 centimeters times 5.2 centimeters is 19.24 centimeters squared. Excuse me. So make sure you combine the units as you do the numbers. Okay, so let's look on the next slide to see why we are going to truncate our 19.24 to 19. Now, if we were doing what we did with addition, we would go to the same decimal place. So I would have probably done 19.2. But with multiplication, I'm claiming I'm only going to go to 19. Since each number has 2 significant figures, the answer has 2 significant figures. Let's see on the next slide why. All right, let's try to demonstrate why I'm going to truncate my 19.24 square centimeters to 19 square centimeters. Let's suppose the measuring devices used to find the length and width have a tolerance of plus or minus 1 I'm sorry, 0.1 centimeter. They are accurate so that the trustworthiness of your measurement is spread for the length from 3.6 to 3.8 centimeters. That's the plus or minus 0.1 centimeter tolerance. The width, which I got 5.2 centimeters, which if also has a tolerance of 0.1 centimeter, means that the actual value of the width is somewhere 0.1 centimeter less than the measured value, which is 5.1, or 0.1 centimeter greater than the measured value, which is 5.3. So now I wish to calculate the area. So I take my measured values, 3.7 times 5.2, multiply them together and get 19.24 square centimeters for my calculated area from the measurements. Now, what would be the minimum value if the measurements were off to the minimum of their tolerance? According to the tolerance of spread of the measured values, the minimum value of the length would be 3.6. The minimum value of the width would be 5.1. If they happen to both be at their minimum, and I multiplied them together as 3.6 times 5.1, I could get a minimum area of 18.36. Let's find if the tolerances are such that the measured values are off so that they are at the maximum they could possibly be. I measured a length of 3.7. It's got a 0.1 centimeter tolerance, so maybe it should have been more like 3.8. The width, instead of being 5.2, maybe should have been up to 5.3. So the maximum area I could have had for the rectangle would have been those maximum values from the tolerance multiplied together. That's 20.14 centimeters. So notice the calculated area from the measured values straddles exactly the values from the minimum and the maximum right in the middle. 19 is what you got, 18 is the below, and from the minimum ones, 20 is what you would have got from the maximum ones. So the error does show up in the ones place of the calculation as we are trying to demonstrate by the way we put these numbers together. So the bottom line is you don't have to worry about all those things we did. As a matter of fact, I think we did some things like that in laboratory where we took the minimums and multiplied them and took the maximums and multiplied them and did things like that in the 1230 lab. But the point would be, when you multiply or divide numbers of significance, the answer that you display has as many significant figures as the one with the fewest. Oh, once again, I'm sorry, I lost my cursor. Again, here when I do those values, the actual value I get using the measured ones straddled exactly up and down 1 unit between the values I get from the using the maximum possible, including the tolerance to find the area, and the minimum possible from the tolerance finding the area. So the answer I would report for the value of the area of this would be 19 plus or minus 1 square centimeter. Now again, the combination of the tolerances is not so important as the example of I started with 2 digits of accuracy in my length and width, so my answer of the area has 2 digits of accuracy as well. So here are some examples of doing such. Now remember, if these units showed, if these measurements showed units, not only should you combine the numbers, you should combine the units. So had they shown them, I would expect you would report the units as the combination of the multiplications or divisions that you're performing. So the first number that I'm multiplying has 6 significant figures. The second one has 2. When I combine them, I get a big long number to the display of my calculator printout, but I only give 2 digits of significance for them. I could round off or truncate it to that second digit. It doesn't matter. That's where the error begins to show up anyways. In the second example, I'm showing dividing numbers of significance. The top number has 4 digits of accuracy. The bottom number has 2, 4, 6, 7 digits of accuracy. And in a sense, you're wasting your time getting 7 digits of accuracy of the bottom number because the combination of these numbers is limited in significance to the 4 significant figures of the top value. Again, when I do the combination, I get a big long number. I truncate or round off the answer until I have 4 digits showing. Again, if there are units for these, I would do the combination of the units as well. In the bottom example, I want you to pay careful attention to this because you can bet you're going to see one like this on the quiz next week. That would be I take this number 80.7576, which has 6 digits of accuracy. I'm going to multiply that by 325, which has 3 digits of accuracy. So for certain, the answer should have 3 digits of accuracy. But when I multiply 80, I went to reach for my calculator. I multiply 80.7576 times 325. My calculator spits out a huge number, 262.46.22. All kinds of digits. First of all, I'm only supposed to report this to 3 digits. If I eliminate some of the zeros, I could report 26200 by putting 2 digits in the positions of non-zeros. But remember what we said, though you would be adding zeros to the number that make it hard to determine where the accuracy begins to a person you're reporting the value to. You do not pad the value with zeros to the left of the decimal place, but none past the decimal place. That's a bad form. So in order to eliminate the padding zeros, you can do one of 2 things. You can change the unit scale to get rid of them, or as I did here, I presented the number as 2.62 times 10 to the 4, which really represents 26,200, but those zeros in the 26,200 can't be shown because of the implication that we're not sure about the significance of those padding zeros. So I eliminate them using scientific notation. Commonly, we perform multiple operations over and over again, and if they're the same type, you just use the same rules. Whenever you add or subtract, the answer has the significance of the one with the fewest number of decimal places. When you multiply or divide, you count the total significance of each number in the combination, and then the answer has the same number of significant figures as the one with the least significance. So what if, for example, we're going to do a combination of operations that require both subtraction and division? Like, for instance, a very common thing we do is calculate a percent error. So I have an experimental volume that I measured for something as 224.0 milliliters. I was able to get its experimental value to 4 digits of accuracy, but somewhere in the literature or the known values for this are given to 6 digits of accuracy, and I'm going to combine to find the percent error of my 4-digit experimental volume measurement compared to the actual known 6-digit volume of this object. So what percent error should I report? So percent error, as you probably remember, is defined as the absolute value of the actual measurement minus the experimental value divided by the actual times 100. So what I'm going to do is perform order of operation here. I'm first going to find the numerator by subtracting 228.483 from 224.0. And when I do that, I use the rules of significance of subtraction. I report the answer in the numerator since I'm doing a subtraction, and the number of significant figures in the least significant number has 1 decimal place. I report the subtraction to 1 decimal place. So now I want to divide that number with 1 decimal place by a number that was known to 6 digits of accuracy. And of course, now I'm doing a division operation. So the rules of dividing are that the answer has as many significant figures as the one with the fewest. So I'm dividing a 6 significant figure number into a 2 significant figure number. The 100, we'll talk about in a moment, is a constant. Doesn't have any significance at all. Really, we could think of that as 100.0000000, because that's what you do to convert decimals into percentages. Anyways, you multiply them by exactly 100. So what I'm going to claim, and I'm going to reiterate on a later slide here, is that I don't worry about that constant having any less than or more than 2. It is actually completely accurate. So since there's 2 significant figures in the numerator, and I'm dividing it by 6 significant figures and multiplying by a perfect number, I'm going to report 1.9% error with 2 significant figures when I did the combination of the operations that you see there. As I just mentioned on the previous slide, in the percent error formula, there's a value of 100 that converts the decimal form into a percentage. That 100 is a constant in the formula that is considered 100% accurate. Even though I'm only showing it with 3 digits, it's 100.0000000. This is true in other formulas that have constants in them as well. For example, the area of a triangle is 1/2 the base times the height. The factor 1/2 in the formula is assumed to be perfectly 1/2, having infinite significance associated with it. So when I'm going to multiply an infinitely significant number by a base measured value by a height measured value, the answer will have the significance limited by either the base or the height. Now, if you use an irrational constant such as pi, now you got to be a little more careful. Pi is an irrational number which itself is known to a certain degree of accuracy. Now, people have been crazy and figured out pi to many digits of accuracy, and your calculator certainly carries pi in it. If you hit the pi button on your calculator to, I would say, at least 7 digits of accuracy. But if you're just going to enter 3.14 and use that as pi, then you're truncating the significance of pi to 3 significant figures. So if you use an irrational constant such as pi, you have to limit the significance of any calculation involving pi to the degree of significance that you limit pi to. If it's a rational constant, as is done in the formula below, then that is an infinitely significant value in that particular case. What do we do in the case of logarithmic values, which we will commonly do, particularly when we start doing pHs and things of that sort? First of all, a logarithm is a value that you exponentiate 10 to in order to make that value possible. So the logarithm of 1,000 is 3 because 10 to the 3 equals 1,000. So that's what the value of a logarithm is. It takes a number and converts it into a form that if you made it into a power of 10, what exponent to that power of 10 must you have to give that number? So when you're doing significant in calculation, how do we use logarithmic values? And again, this is going to be important when we start to do pHs and things of that sort. So because the power of 10 to multiply a number by is to the left of the decimal point when you exponentiate this logarithm, then all the decimal places are the ones that figure into the number of significant figures. Now, what do I mean by that? A little confusing, I agree. The log of the number 12 in my calculator spits out to be 1.087918, blah, 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 blah. How many significant figures do I ascribe to that? Well, the power to the left of the decimal place of the logarithm is how many times 10, since this is a number bigger than 10, 10 to the 1 is 10, so this has to be an exponent at least bigger than 1. And so then where do the connection between the significant figures and the significant figures of the measured 12 come in? They come in to the decimal point of the exponential form. So I have 2 digits in my measurement of 12, so I have 2 decimal places in the logarithmic reading to reflect those 2 decimal places. If instead I had log of 12.0, which is accurate to 3 decimal places, I report its logarithmic value to, looks like 4 digits, but really 3 decimal places of accuracy, reflecting those forms of the exponentiated power to which 12 has to be, or 10 has to be expressed to equal 12.0. 12.00 with 4 digits of accuracy has 4 decimal places to its logarithmic form. The 1 stays steady, the other 4 remaining digits are telling you how to get 12 to 4 digits of accuracy and raise exponentially the power of 10 in order to equal 12 to 4 digits of accuracy. So please keep that in mind, that when we're doing logarithmic quantities, the answer has as many decimal places as the value you're taking the logarithm of. Okay, so this idea of transcribing the accuracy of a measurement from a digital readout is quite simple. The digital readout will only give you the values of measurement for the device limited to the tolerance of the device itself. So you simply write down every digit on the display, and that simply therefore indicates the significance of the measurement shown from the device. The error in the device is assumed to show up in the last digit of the readout. It doesn't give you infinite significance. The last digit has either been rounded down or rounded up in order to eliminate the values that go past that, because that's where the limit to which the measuring device can handle it. Okay, so this is going to be true with pH meters, digital thermometers, all sorts of things like that. And typically when you buy a device, you get a manual with it for its operation, and somewhere in there you're given the manufacturer's tolerance. That is the degree of trustworthiness or the uncertainty to the readout that you can expect to trust your measuring device accurate to. So for instance, suppose I go to 3 different stores and buy 3 different scales at 3 different costs. So I go to Dollar General and I buy a scale for $1. I put an object on it and it spits out 1.1 grams. And let's suppose the manufacturer's tolerance suggests that this is accurate to plus or minus 0.3. So that means that the trustworthiness of the answer that I got was somewhere between 0.8 and 1.4 for that measured value. And if you read this statistically over and over again, you're going to get values that range over that spread. Of course, bunched up towards the more likely to be closer to the middle than to the fringes of 0.8 and 1.4. Let's suppose instead I go to Walmart, instead of spending $1, I spent $10 on a scale, and it says it has a readout trustworthy to 0.03 grams. And I put the same object on there, now it spits out 1.12 grams. Now that would be trustworthy then over a spread of measurements of the same thing. Now from 1.09 for the minimum, that's 0.3 minus my measured value, up to 1.15, which is 0.03 plus that measured value. So that's where the tolerance comes in to the level of degree of accuracy of the measurement. Now let's suppose I went to Dillard's and spent $100 on a measuring device, put my same object on there, it spits out 1.123, and in the manufacturer's tolerance of the reader's manual or owner's manual, it says it's accurate to 0.003 grams. So the trustworthiness of my measurement of the device on this, of the object on this scale would be between 1.120 and 1.126 grams. Notice how I'm honing in on the accuracy of the measurement. Notice also I've spent decidedly more money to get a more accurate reading, and that's to be expected because of the fact that you got to pay about 10 times as much for each digit you want. You pay $1, you get 2-digit readout. You pay $10, you get 3-digit readout. You pay $100, you might get something like a 4-digit readout. It scales up accuracy with cost, of course. Okay, that's all fine and dandy with a electronic measuring device like a digital thermometer or a pH meter or a voltmeter. What happens if it's an analog device, something with a dial or a needle that deflects, or even something quite as simple as a beaker or a burette or a graduated cylinder or a ruler? We do these kind of measuring devices all the time. There is no digital readout to tell you where to report the number to. You have to decide the degree of accuracy to which you make measurements and report measurements with them. Because remember, the number of digits you report reflects the degree of accuracy of the measuring device. So let's review the rules for how many digits of accuracy you should report for normal analog measuring devices that you must read without the help of a digital readout, and you are responsible for reporting values measured from them to your upper authorities or whatever. So the rules you follow to take a normal measuring device and report the degree of accuracy on it are shown here on this slide. Now I could read these things to you and bore you with that. I think it's best if we just go to a few examples on the upcoming slides, and I will follow these steps on those slides and show you in practice what you're going to do when you have normal measuring devices in the laboratory. Okay, here I have some kind of beaker or graduated cylinder that is filled with a fluid, and I am supposed to report the value of the reading of the volume of the fluid in the device accurate to the limit as to which the device allows me to report. I'm going to now follow the rules stepwise that were printed on the previous slide. First thing you do is you note the calibration scale on the measuring device. What do I mean by that? You look at the graduations, as they call them, the etchings that have numeric values on them, and I note that this volume device is etched every 10 milliliters. So those are points of reference as to when I pass 10 milliliter, 20 milliliter, 30 milliliter, and so forth. So if the volume liquid level, of course, is above one of these lines, I have a little bit more than that particular value. If it's below one of these lines, I have less. Now let's also note the interesting property of the surface of the liquid too, because the surface of the liquid is known as the meniscus. That's where the interface between the air above and the fluid in the container is. Now it turns out, excuse me, that the closer together you place the walls of this container, the more dramatically curved that surface becomes. That's because the polarity of the glass attracts the polarity of the water in the fluid probably and drags the molecules up the sides, defying gravity a little bit. The attraction they experience allows them to be pulled up by attraction to the glass molecules, and they make a curved surface. This is known as meniscus. So the further apart the walls are, the less obvious the meniscus appears. The closer together the walls become, the greater the curvature of the meniscus becomes. This becomes really dramatic in a burette, and you can really see it very, very dramatically in a burette. But in a beaker with the walls pretty far apart, you almost can make no notice of the curvature of the meniscus. So if there is a meniscus, I would say read from the bottom, do it consistently, always make the measurement from the bottom of the meniscus. Okay, here in the case where the walls are far enough that the surface looks flat, it's going to appear to have the same reading no matter where I look at it from. So, since it's ruled every 10 milliliters, I guesstimate that since I'm between 10 and 20, of course I have more than 10 and less than 20. I guess one place past the calibration. I will guess in the ones location. I'm going to say it's a little more than halfway there. So I'm going to call it 16 for the 6 milliliters representing the distance between the line 10 and line 20. Now you might think it's more like 15, halfway between. You might think it's 17, a little more than that. That's the whole point. There's error in this last digit. I can't go any further than this one's position because I only know the 10's positions for sure. I only know I'm more than 10. I only know I'm less than 20. I guess one place past what I know for sure. Period. End of story. That's what you do. You look at the calibration, you look at what you know, you guess one place beyond, and that's where the error begins in your guesstimate. So I'm going to guess 16, others probably guess 15, others probably guess 17. That's where the tolerance of the measuring device would come in. If the beaker has a tolerance of plus or minus 2 milliliters, then the actual value, I reported 16, would be probably most likely between 14 and 18 milliliters. And the vast majority of people that would report the volume from this device would report values in that range. So again, bottom line, look at the calculations, or look at the device, look at its graduations, guess one place past the graduations, guess no place more. Only one place beyond what you know for sure. Here in the case of this ruler, I note that the calibration of the device is every 1/10 of a centimeter. The etching, the spinous etchings on there represent 1/10 of a centimeter. I notice that I am somewhere between the mark 2.7 and between 2.8 at the arrow where I'm supposed to make where I'm supposed to make the measurement. The arrow is located a little further than 2.7. The arrow is located a little less than 2.8. So I know the correct answer is greater than 2.7 but less than 2.8. I guesstimate one place past the known value. So I'm going to say I'm about 4/10 of the way from the 0.7 to the 0.8. So I'm going to call it 2.74 centimeters. You might call it 2.73. You might call it 2.75. That's okay because the error is in the hundredths place of a centimeter as the device is showing me. So again, if this happened to have a tolerance of 0.01 centimeter, then the vast majority of readings would be somewhere between 2.73 and 2.75 that are reported for the location of the arrow that I'm using to make this measurement. Okay, once again, I'm sorry, but I must be auto-saving because again, my cursor disappeared. Let's recall the usage of the burette, which is going to play a prominent role this semester like it did last semester. First of all, you fill the burette at the top. You dispense liquids out of the burette at the bottom. For this reason, the burette has the characteristic that it is numbered in reverse to a beaker or a graduated cylinder. Beakers and graduated cylinders begin with 0 at the bottom, and they go up to the maximum volume at the top where you're emptying it from. Since you empty the burette from the bottom, 0 on the burette is at the top, and the maximum volume of the burette is at the bottom. Not only is this true, as you read the burette, you read downward, backwards, the value of volume that is represented off of the burette. Now, the other thing to keep in mind is because the walls of the burette are so close together, there's typically a very dramatic meniscus, curvature of the air-liquid interface due to the polarity of the glass pulling on the polarity of the liquid. So first I suggest reading from the bottom of the burette. Second, I state that it is ruled to the 10th of a milliliter. So you report to the place beyond that. The place you're guessing is in the hundredths of a milliliter. Now again, because it is ruled in reverse, you read bigger numbers going downward as compared to bigger numbers going upward. So when the burette is full as shown at the top, and I explode the diagram to look closely at the readings, I note that the volume is between 7 and 8 milliliters. Now remember, the very top is 0. So I'm going downward, 0, 1, 2, 3, 4, 5, and I'm between 7 and 8 on the way down. So I'm between 7.1, I'm between 7.3 and 7.4. I know that reading is below the point, well, it's representing bigger than 0.3, but less than 0.4. I'm going to guess 8. The bottom of the meniscus is 8/10 of the way between the 3 and the 4. So I'm going to report 7.38, heading towards 8. Now you might say that's a little, not quite that far. That's right there, whatever the tolerance is. All you and I agree upon is that this is ruled to the tenths, you report to the hundredths. So then I put a beaker under it, and on the bottom exploded diagram, I poured liquid into the beaker from the top full burette. The volume has run down, the numbers are getting bigger. I am now between the 44.3 and 44.4 marks on the graduations of the burette. And again, I'm going to claim the bottom of my meniscus is about 8/10 of the way from the 0.3 to the 0.4 mark. So I'm going to say 44.38 milliliters for the final volume reading, accurate so that the error shows up in the hundredths of a milliliter on my burette. Now, if I'm asked to report delta V, which is VF minus VI, I would subtract 44.38 from 7.38, and when I do so, I would report the answer so that it has the number of decimal places as the one with the fewest. Since they each have 2 decimal places, I report the volume difference in the reading of the burette to 2 decimal places of accuracy. Okay, here's an example of 2 volumetric devices that are both accurate as displayed on their readouts, even though they look quite different. They're both ruled every 1 milliliter. Okay, well, one of them doesn't have them each individual milliliter marked out as on the right, but you can tell from the values presented in the device that certainly I know the limit's 50, 60, 70, but there are graduations to indicate between for 51, 52, and so forth happen to be on the device on the left. So each of these devices is ruled to 1 milliliter. The one on the left, I see that the meniscus is between the 62 and the 63. So I'm going to say I'm about 8/10 of the way up the hill there. Maybe you wouldn't say that, maybe you would. So I'm going to then report 62.8 to give the value. Maybe you thought it was a little closer, maybe you thought it was a little further away. That's when the manufacturer's tolerance comes into play. And I'm saying the vast majority of people would report that between 62.5 and 63.1 milliliters based on the tolerance of the device. The one on the right has the same graduations of 1 milliliter each, but the spacing between them is so much greater, it allows the tolerance, as you note, to be smaller. There's a smaller tolerance in the one on the right because the spacing between the graduations is greater. So I can get a more accurate reading of between the graduations of the one on the right compared to the one on the left. Still, I note it's above 8, it's below 9. I'm going to claim I'm about halfway between 8 and 9, so I would report 8.5 milliliters. Now, this one's got a tighter tolerance because it's more easy to tell how far you are away from the 8, and you should be a little more accurate in your reporting collectively for a bunch of readouts. So this has a smaller degree of inaccuracy, as you see, for the milliliter readings compared to the one on the left. The vast majority of people would report this between 8.4 and 8.6 milliliters. Some further examples here. I'm using a scale ruled to the 10th of a gram. That means a report to the hundredths. Since the arrow indicator is slightly above the 17.4, I'm going to claim 2/10 of the way between the mark of 0.4 and 0.5. I'm going to report 17.42 grams. If the tolerance happened to be posted, that this, if no tolerance is posted, the minimum error I could have is 0.01 gram in my reading. The minimum spread of the answers from my value of 17.42 would mean that the value should fall between 17.41 and 17.43. Now, in the case on the right, again, I'm using a meter stick that is ruled to the 10th of a centimeter. I want you to note very carefully, the arrow I'm supposed to read on is directly on the 3. However, due to the rulings of 1/10 of a centimeter, I'm required to report my measurement of length accurate to the hundredths of a centimeter position. So I am going to report 3.00. You might want to say 3.01 because it's slightly off the one, maybe ever so slightly. But in any regard, the value you report should be to the hundredth of a centimeter accuracy because the device is known with ruled values to the 10th for certain. And I'm guesstimating the position afterwards. This is, again, a reason why metric are preferred, because the metric values are scaled in powers of 10. So I can simply go in tenths of a degree away from between the graduations to most easily represent and estimate the unknown inaccurate digit that I'm supposed to include in my report. One final set of examples here where I'm using beakers to report the volume of liquid in them. Now, unlike the burette, these are filled from the top, empty from the top. They are graduated and ruled, starting with 0 at the bottom, going up to the maximum value at the top. I note that the beaker on the left is ruled to the thousands of milliliters, 1,000, 2,000, 3,000. I note that the volume is greater than 2,000, is less than 3,000. The inaccuracy I should report is in the hundredths of a milliliter position. I want to be clear to you. If I report 2700 milliliters, that shows inaccuracy in the reported value. The zeros you're putting there make it unclear whether those are measured zeros or just padding zeros to put the number to where it should go. So, if you are going to report the volume correctly in this beaker, you have one of two options to eliminate confusing zeros. You're unsure if those zeros are accurate or not when you see the reported value 2,700. I can either change the unit scale from milliliters to liters, because there's 1,000 milliliters in a liter. I could divide that number by 1,000 and convert my 2,700 milliliters into 2.7 liters. No padding zeros, indisputably 2 digits of accuracy. Error in the hundredths of a liter position, or I'm sorry, in the tenths, of a liter's position, which is in the 100 milliliter position. Or I could equally do this, leaving the units in milliliters by eliminating the padding zeros by converting my 2,700 into 2.7 times 10 to the 3 milliliters. Again, I do not put the zeros after the decimal point. Those would indicate accurate zeros. And according to my reading, those are inaccurate zeros, so I leave them off. In the beaker on the right, which is graduated every 100 milliliters, I note that the volume that is placed in the beaker is more than 300, but less than 400. I'm claiming I'm a little more than halfway towards the 400, so I'm going to call that 360 milliliters. However, I do not recommend you report in that fashion of 360 milliliters. Either change the unit scale by dividing your answer by 1,000 and report 0.36 liters, or leave it in milliliter units but report it in scientific notation to eliminate the padding zero that creates ambiguity. I could report this as 3.6 times 10 to the 2 milliliters. You pick which way you would wish to do it. So when we when we reconvene for class next week, beginning at the very beginning of the period, there's going to be a quiz covering these skills where you will be asked to perform various operations that we've seen so far on these slides. And that will happen right at the beginning of time before we begin the business of our class for that particular day.